he holds currently the Canada Research Chair in signal processing in the ECE department at the University of British Columbia. His current research interests include social networks, computational game theory, and stochastic control. He served as an IEEE DL in signal processing, and also as the editor-in-chief of the journal Selected Topics in Signal Processing. And in 2013, he was also awarded an honorary doctorate from KTH in the Royal Institute of Technology in Sweden. Dr. Krishnamurthy is actually very well known in the SP community, and he's been contributing in many different ways. And it's a pleasure to have him here for coming.
Thank you, Hamid.
The floor is yours.
Thank you very much. So I apologize for the little time delay in setting this up. It's more Windows-centric than Apple-centric, but that's okay. So the title of the talk is Sensing and Decision-Making in Social Networks. And of course, that's a huge area. And this talk is really using tools from statistical signal processing, a little bit from microeconomics, and some ideas in stochastic control. So it's really an electrical engineering focus on that, with some ideas of microeconomics sprinkled into that. So how do I scroll? I guess I just press the mouse once? Or?
You can actually use your finger.
Here?
Yeah, you can push that arrow.
Huh?
Yeah.
Okay. Yeah. Really high tech. That's
okay.
Yeah. So I first want to start with just some basic loose definitions of what we're describing here. So let me first start with something about a social or a human sensor. So a social sensor typically is a human, and it provides information about the environment to a social network after interacting with other humans. So you can say other agents. So agents and humans are used, same terminology. And examples of this include, of course, Twitter, Facebook state updates, ratings on online reputation agencies like Yelp, TripAdvisor, several other things as well. Now, it turns out there are actually some big differences between social sensors compared to standard sensors we encounter in electrical engineering. There are some substantial differences, and it's worthwhile, at least at the beginning of this talk, trying to explain why they're different before we go into any mathematics. So first of all, humans influence other humans for a start. So in a sense, what we're saying now is that one sensor can influence the observations and decision-making of another sensor. Okay, so that's the first difference. The second difference is, if you go back to your undergraduate or graduate student days, you will know that when you describe a standard dynamical model, the dynamics are in the state, and your observation equation, which is the sensor, is usually a static equation. It's a state embedded in noise. It's a static equation. Well, it turns out that when you're dealing with humans or social sensing, the sensing has its own dynamics. The sensor really learns from previous decisions and from its own private observation. So the sensing itself has dynamics. So at least from a modeling point of view, it introduces quite a lot of interesting mathematics because it has its own dynamics. The third point is that sensors, at least when they're humans, rarely disclose all the information content. This is due to privacy reasons. TripAdvisor has ratings, good or bad. You don't actually describe the entire nature of a movie. That would require putting the entire movie on the web. You don't do that. You just give a rating. And usually these ratings are ordinal. Humans make ordinal decisions as opposed to cardinal decisions. So ordinal means if I were to eat out in a restaurant and it costs $200 or it costs $201, it doesn't really matter either way. It's targeted as expensive. So the cardinal value 200 or 200.56 is irrelevant. The ordinal decision is that it was expensive. So humans usually reveal quantized ordinal decisions. And this has to go into the modeling if one were to construct a mathematical model for this. And finally, these social sensors also go beyond physical sensing. And there are several examples for that. So for example, if you were to go to TripAdvisor, if somebody rates a movie, it is actually very difficult to construct physical sensors to rate a movie. You need a human being in the loop somewhere to come up with a rating. Okay? So there are substantial differences between the way you model a social sensor and the way social sensors interact compared to sensors in standard signal processing. This little graph here actually shows us what we're going to talk about subsequently in this talk, where we have sensors which possibly record either red or green. This could, for example, be the propagation of disease in a human social network, like a health network. Somebody red might have the flu, somebody green may not have the flu. How does the dynamics of propagation of information take place in this? Okay, that would be something we will consider later. Now, one can also think about the idea of how do you mathematically, at least in simple terms, construct a model for these individual sensors, human social sensors. In the simplest setup, and we're going to refine this as we go along in the talk, a standard signal processing sensor is where I have a signal corrupted by noise, and that noisy measurement is a sensor. The aim of statistical signal processing is, at least in its most abstract sense, I have this noisy measurement, and I devise an algorithm which processes the measurement to come up with an estimate. That's really all signal processing does. I come up with something sophisticated which eliminates the noise to estimate the signal. The difference now is we have a sensor which reconfigures its behavior in real time. So the sensor comes up with an estimate. The estimate is used to make a decision, because a human reveals only decisions, as we said. Going from an estimate to a decision is something like a quantization, which actually involves optimizing a local utility typically. And this is usually an ordinal decision, as we said, and it is this decision which feeds back, for example, to other sensors. So it's actually quite an interesting setup, even from a stochastic control point of view. In a standard signal processing, we just have the open loop, the sensor, the algorithm, the estimate. In stochastic control, the estimate feeds back to a controller, and you can reconfigure the sensor. We have another thing here where you have a local utility as well, which is optimized. So this actually is even more general in some ways, and we will describe all this in more detail as we progress through the talk. So here's an outline of the talk today. There are two parts to this talk. I know there's a part 3 here, but I'll just kind of mention this part 3. I won't describe it in detail because there won't be time. So the talk today has two parts. The first part deals with how do agents learn from the observations and actions of other agents. So this is a very simplified setup of the framework of how humans sense stuff. And we're going to use a very powerful model which has been developed in the economics literature a lot, called social learning. Okay, and we're going to describe what that is. The reason why this is very interesting is that you have very unusual behavior coming out of this, and so it's always interesting to see something unusual. Things like herding and data incest occur, which I will describe. So that'll be the first part of the talk. We deal with a known structure of a graph in a social network where agents exchange information, and we're going to model that using this. In the second part of the talk, we're going to deal with very large social networks. So large graphs asymptotically where the number of vertices or the number of edges go to infinity. Okay, so we've got to deal with very large graphs. These graphs are used to look at how, for example, a technology propagates or a disease propagates. So these are social networks. And of course, if binary valued information propagates in a large graph, that is a very complicated combinatorial object because you have to list every possibility in this graph to kind of track what's going on. What we're going to show is that you can asymptotically use something called mean field dynamics to replace the dynamics of this horrible combinatorial object by a differential equation. And a differential equation is a much easier animal to deal with. So that's the mean field dynamics. People have developed mean field dynamics in game theory and so on. We're going to talk about it here just in the sense of tracking information in a social network. As I told you, those are the two main parts of the talk. There could have been a part 3, but I won't talk about it due to time constraints. But let me just tell you what part 3 would have been had there been time. So in both these parts, one of the implicit assumptions made is that at each stage, a human makes a decision based on optimizing a utility function. And of course, the first question somebody is going to ask you is, do humans really optimize a utility function? If I give you real data, how can you tell if humans have optimized a utility function? So there is this very powerful tool in microeconomics called the principle of revealed preferences. And if you Google it up, you'll see it's a huge area. And roughly speaking, it deals with the following problem. Suppose there was a black box. And into this black box, at each time, I could feed a time series called a probe vector. So at different times, P of t is the input. It's a vector at each time. It's a time series. And corresponding to the input, I could look at the response of the system, x of t. Okay? And then my question is the following. If I look at P of t and x of t, can I decide if this black box is rational? So, of course, I need to define what I mean by rational. Well, in a mathematical sense, can I answer the following question? Was the output x of t the output obtained by optimizing a utility function? In other words, does there exist a utility function such that x of t is the argument of the maximum of the utility function, subject to a constraint between p and x, which is linear typically? That constraint is not so important. Actually, you can see that's a pretty deep philosophical question, because normally in electrical engineering, what we do is the reverse. We have an optimization problem, we optimize the hell out of it and get an answer. Here we're doing the reverse. We're looking at an output, and we're asking, is this output the result of optimizing a utility function? And the answer is yes, you can answer this question. There's a yes or no test, which was developed by a very famous economist in the 1970s. And in fact, the chief economist at Google, whose name is Hal Varian, has done a lot of work on this recently to use this to go through big data sets in advertising in Google and so on. So I would have talked about it, but we don't have time. I'm going to talk about the first two parts. But if you're interested after this talk, I'll be happy also to describe part 3. So we're going to go on to parts 1 and 2. Before I go into the details, it's worthwhile telling you a little bit about what might be the unifying theme between these two parts. Well, the unifying theme between these is that, of course, sensors have dynamics, as I said, because these are social type sensors. And another really important unifying theme is the following, that each human as an individual is making simple decisions. At least that's the paradigm we're assuming here. And the question is, if every local system makes simple decisions, can the interaction of simple behavior result in something which is sophisticated in its behavior? And that is really the question. Simple local behavior, can it result in sophisticated, or if you like, rational global behavior? People in game theory ask that question, and really we're trying to answer that using some simpler tools than game theory in this talk. And of course, another point here is that the information patterns, as we will see in this decision making and signal processing, are non-standard due to exchange over a social network. Okay, so those are the sort of introductory comments. Now I'm going to go on to part 1, which talks about social learning. Okay, so if you try to understand the area of social learning, you will see that it's a huge area. There's a lot of work been done in that. In fact, there are several communities who have contributed to the area of social learning in the last 20 years or so. Psychology, economics has done a lot, sociology, computer science, signal processing, and so on. Okay? All these communities work in this area. There are numerous famous papers in this. There are also several books. One really good book for those of you who might be interested in this area is a book written by an economist, Christoph Schamli. It's called Rational Herds, and this is a very, very nice book. The whole book deals with social learning. There's also a very good popular book, The Wisdom of Crowds, written by James Surowiecki. This really deals with social learning to the layman, and I'll say a bit more about it later on. In this part 1 of the talk, we're going to have 3 subparts. The first part, I'm going to talk about how you can model social learning in a Bayesian context. So really, this entire part 1 is Bayesian. We're going to assume that agents are Bayesian. Then we're going to talk about how you can do global sensing with social learning. And then I want to very briefly describe what is data incest in social learning. So these are the 3 subparts of part 1. And part 1 is purely Bayesian, as we will see. It's using Bayesian signal processing. So let me first describe the basic social learning model, and then I'll come to this. So I want to first start with vanilla social learning, the simplest form of social learning. So what we have here are a bunch of agents, okay? And we index these agents by time k. So k equals 1, 2, 3, and so on. K can also be thought of as time because each agent acts only once. So agent 1 acts at time 1, agent 2 acts at time 2, and so on, okay? So this is the simplest setting. You can have more sophisticated settings where agents act multiple times, but this is a short talk, so we'll assume that each time one agent acts at each time. And their aim is each time an agent acts, it's doing something so that eventually this bunch of agents want to estimate a random variable x, which takes on one of a finite number of values. Again, this is purely for simplicity. This could have been a random process rather than a random variable. We made it a random variable purely for simplicity. Okay. So this is one of x possible values. And this is the protocol of social learning to do that. So this is a standard protocol people study in economics and social learning. So at time k, I have the prior of what my state, which I'm trying to estimate x, given the decisions of the previous agents a1 to ak. So I know the previous decisions of agents. Okay? So one guy might have said good, one guy might have said bad. I have all the decisions of k previous agents. And this is my prior. I call it pi of k. Whoops, hope I didn't do anything there. Okay. Now I am agent k plus 1. Okay, I want to describe what happens. So what does agent k plus 1 do? Agent k plus 1 has this prior. It gets a private observation yk plus 1, which is basically the state and noise. Okay, so there's a prior. Now, the standard Bayesian system, of course, is as soon as I have an observation, I compute the likelihood. I combine the likelihood with the prior using Bayes' rule, and I get a posterior. That's all Bayes' rule is. I multiply a prior by a likelihood, I get a posterior. That's trivial. That's what Bayes' rule is. Here there's a little interesting twist in social learning, and that's why it's such an interesting problem. So what the agent does, of course, is it gets its observation yk plus 1. And now it has to make a decision based on that. So the decision it makes is it chooses a decision to maximize or minimize, in this case, a local cost function. Okay, every agent is a utility maximizer. So there's a local cost function, c of x comma a. It doesn't know x, of course. So the best it can do is optimize the conditional expectation of c of xa. Given the past decisions of previous people, it knows that from the prior, and its private observation. Okay? This is basically classical Bayesian stuff. So it computes this. It finds the best a which minimizes this, and this is the decision agent k plus 1 takes. Okay? It's very simple. And then it broadcasts its local decision to the next agent. Now, of course, we need to go from pi k to pi k plus 1. Well, that's pretty easy. Once the local decision of agent k plus 1 is known, then all the agents update the public belief, which is pi k, by Bayes' rule. So they compute pi k plus 1, which is now the probability of the state given a1 to ak plus 1, as a function of pi k using Bayes' rule. Okay. Now, I need to point out something which is quite spectacular about this very simple concept. It looks trivial at first sight, but there's something very interesting here. Okay. So if you think about standard Bayes' rule, where you simply sent your observation to the next guy, you combine your observation with the prior, it would just be a product of the likelihood times the prior. Now the main difference is, of course, that you are not directly sending your observation to the next guy. You're using your observation to take an action, and you're sending the action to the next guy. Okay? What that means in Bayes' rule here is that your posterior is the probability of picking an action given your observation and your prior times the likelihood times the prior. Now look at this box enclosed in red. In standard Bayes' rule, this would be a likelihood. Now this is a likelihood of the action rather than the observation. But something very spectacular in this red box is that your likelihood now is an explicit function of your prior. It's not true in standard Bayes' rule. In standard Bayes' rule, your likelihood has nothing to do with your prior. It's simply the probability of your observation given the state, which is a function of the noise. Because of the social learning where your action depended on your prior, this guy depends on this. And it is because of this reason some spectacular stuff happens. And let me tell you what happens. So here's a famous theorem, which if you look in 1992 Journal of Political Economy, which kind of opened up this area. And it says the following. So as an engineering student, you can easily code this up. It's about 3 lines in MATLAB. And you'll see something very interesting happens. After a finite amount of time, all agents will simply end up taking the same action. They all form a herd. In other words, an agent completely disregards its observation. It simply parrots what the previous agent said. In other words, after a finite amount of time, with probability 1, all these so-called rational agents become irrational. They completely throw away everything about their observation. They simply mimic what the previous guy said. And I'll give you a bit more of a description as to why this is the case, and I want to make a few comments.
So is it assumed that all agents have the same cost function?
In this simplistic case, yes. So I'm giving you I'm going to describe after this more sophisticated versions of this. So in the most simplistic setup we have now, this is a linear graph. Each guy propagates only to the next guy. You could think of a more general graph in detail. In the simplistic case, everybody has exactly the same cost function and the same measurement distributions. You can think of a more sophisticated, and I'll come to that later. So this is the main theorem. And just to repeat, this is what it says, that agents eventually choose the same action. That is called an information cascade, and more colloquially we'll call it a herd. Actually, there is a little subtle difference between them, but we'll assume they're the same. And I want to give you some intuition as to why that's true. Okay? Yes?
Do you consider the notion of punishment and reward in this settings?
In the simplest case, no. In the next slide, yes. So I will describe next slide what I mean by optimized social learning, where people get rewards for this. But not yet, not in this case. In this case, people only have a reward for taking their local action. So every agent here is purely capitalistic. They have their own reward, they just take an action, and then the next guy does something. Okay, so what is the proof for this? Well, the proof of this uses actually elementary ideas in martingales, but I won't even go into that. I just want to give you some intuition into why this is the case. It turns out that the martingale argument simply will show you that as k gets larger, at some finite amount of time, this guy here is going to be independent of y. Okay? So the probability of taking an action given my private observation and the belief after some finite time, and you can show that the martingale argument, gets independent of y. So this guy comes outside the summation. If I add p of y given x over y, it gives me 1. So in other words, pi k plus 1 is equal to pi k. What happens, in other words, is my Bayesian update hits a fixed point and it doesn't change. Essentially, learning stops. I cannot get any better. I just stop. All the next decisions are exactly the same because the actions reveal nothing useful anymore. Okay, so the actions people reveal are completely useless. That is really the proof, and it's actually a pretty straightforward proof. As I said, I've given you the most simplest setup here. There is a more general paper by Asimoglu and Ozdagler published in 2010 where they look at more general communication graphs. And again, you have the same kind of herding. Now, I want to make several comments on this before we jump out of this page to give you some intuition. Here's a simple form of intuition of this. So you're sitting at home and you're too lazy to check the weather forecast. You see some guy walking down the street with an umbrella. That person is rational. You assume that person checked the weather forecast. That person thinks it's going to rain, therefore they was carrying an umbrella. So therefore you take an umbrella. So now there are 2 people walking down the street with umbrellas. Some guy sitting at home says, oh, there are 2 guys walking down the street with umbrellas. It's probably going to rain, so I'm going to take an umbrella as well. And so there are 3 people and so on. The point being that the first guy who took the umbrella could have taken it for no apparent reason whatsoever. So it could be that everybody formed a herd to the wrong decision. Okay? Another famous example of this is a so-called restaurant problem. I'm a stranger here to the city, and if I go past a couple of restaurants, I might see one of them is empty, one of them has a lot of people. I will assume perhaps the one with a lot of people is good, so I go in there and it gets more and more people. So that's again a form of herding. Okay? Now, in the restaurant problem, you can break the herd pretty easily by paying actors to sit in your restaurant to pretend to be customers, and that could attract people and so on. That's called mechanism design in game theory. I won't go into the details here, but you can imagine there are innovative ways of breaking herds.
One other
yes.
Very, I think, naive question. I mean, so why did you consider Bayesian belief update instead of reinforcement learning, like policy learning?
By policy learning, you mean we're taking a stochastic control problem and optimizing a cost? Yes, that's coming up. So again, I'm going to show you that when I talk about constrained social learning. Yeah. This is the simplest version so far. I want to make one more comment on this before I jump to the next page. So here's a famous example of herding. So in 1995, a couple of guys wrote a book, and it had very mediocre ratings. So what they did was they secretly bought 50,000 copies of their own book. Overnight, it became a bestseller in New York Times, and then people started buying the book because it was a herding behavior. Again, that's an example where if I know the private observation why, that is, who bought the book, I would know it's the author, and then I knew there was no reason to buy it. But all I see is the action, how many books were sold, and therefore I mimic. So this form of herding can be used by malicious agents to deliberately cause people to make wrong things. And so in sensor networks and so on, or in social networks, you can think of bots which deliberately go into social networks and try and create spam to cause all kinds of havoc. There are all kinds of ways you can think about this setup. Okay. So that is like the basic vanilla version of social learning. You have a sensor, a Bayesian filter. This is basically a Bayesian filter for pi k, a local utility, and we're taking an action. That's what we've done so far. Now, in a more sophisticated setup, what we can say is we want to close the loop and have a controller which decides how long do I do this procedure before I stop. And that's coming into reinforcement learning and stochastic control, which I'm going to describe next. Okay, so now I want to talk about a more sophisticated problem where how can multiple agents that are doing social learning come up with a decision of a global variable? What do I mean by that? So I'm going to illustrate this actually with something called quickest change detection. Quickest change detection is one of the simplest examples of a stochastic control problem. So first I'm going to describe the basic quickest change detection in the classical sense, which has been known since the 1950s. And then I'm going to show you what happens when you apply social learning to this problem and how it makes a substantial difference. So let's first talk about the basic multi-agent, the basic quickest change detection problem. So the classical quickest change detection problem is a single agent quickest change detection problem. And it goes as follows. I have a bunch of observations. Until some random unknown time tau 0, the observations come from a distribution B1. After the random time tau 0, they have a distribution B2. So there's a change. Okay? It's a change detection problem. Tau 0 is the change time. Everything here is Bayesian. So we're assuming that tau 0 has some known distribution. Usually it's assumed to be geometric in the simplest case. It doesn't have to be. It could be anything with a known distribution. Now the aim in quickest detection, of course, is to try to decide when tau 0 occurred as quickly as possible. So me as a decision maker, I say that the change happened at time tau, and I want to get tau as close as I can to tau 0, which is a true change time. And what do I mean by close? Well, I pay a penalty if I don't get it close. So suppose I say I'm going to wait for a lot of time, and then the more time I have, of course, the better off I can decide when the system changed. I pay a delay penalty. So if I wait till time tau and the system changed at tau 0, if I wait a lot, I pay a delay penalty. On the other hand, if I'm too trigger happy, and I say the system has changed before it's changed, I pay a false alarm penalty. Okay? So it's a trade-off between delay and false alarm. This is a classical stopping time problem. It's a stopping time problem because the moment I decide the system has changed, my problem stops. I've decided the change has happened. So this is called a stopping time stochastic control problem. It's one of the simplest types of stochastic control problems out there. This problem has been studied in great detail since the 1950s. Shiryayev actually has a complete result for this in the 1950s. And basically the answer is follows again. It's a Bayesian solution. I compute my posterior probability, pi of k, which is a probability of change given my observations, y1 to yk. That is this axis here. Okay. So this is a probability I compute using Bayes' rule at each time. Every time I get a new observation, I update pi k. This vertical axis is the decision I make. So as my posterior probability gets closer and closer to the right-hand side, that is, the probability of change gets larger and larger, eventually there's a threshold beyond which I declare a change. And this is the optimal structure. This is actually pretty easy to prove using dynamic programming arguments. And it's very intuitive. Of course, as the probability gets larger, you should declare there's a change. Okay, so this is trivial. Now, Let's take the same problem and analyze it in the case where instead of pi k being the probability of change given the raw observations, pi k was the probability of change given the actions of previous individuals, which is what social learning is. Okay? So let's just quickly analyze what happens there. So let me again kind of actually scroll back one slide to give you a bit of motivation into that. And so I'm just going to jump back to the previous slide and then I'll come back. So let's understand what we're doing here. So now we're trying to decide, has the system changed or not, right? That's the quickest detection problem. And we're doing it with social learning. Remember, social learning as a sensor, a Bayesian filter, a local utility, which was a local action. The quickest detection, if I'm trying to decide if the system changed or not, is like a controller. It's deciding either I stop and decide a change happened, or I continue and take more measurements. So I have two choices. So this is really a very interesting setup. I have a local decision maker here, every individual deciding on their actions, and a global decision maker which uses the local actions to make a global decision. Do I stop and continue? The local and global decision makers obviously interact because the global decision to continue implies the local decision maker has further observations. So of course the two interact. And the local decision maker's local actions of course decide what the global decision maker makes, because the global decision maker only has access to the local actions. Okay, so it's an interaction of two decision makers, local and global. Okay, I just thought I'd mention that. Now let's go back to the quickest change multi-agent case. So the agents perform social learning, and they compute the probability of change given the actions using the same protocol I mentioned in the last page. They take a private observation, they take an action which minimizes their local cost, they perform social learning. Now the question would be, what is the optimal policy for the global decision maker now to decide if a change happened or not? And here is something which is very surprising at first sight, and this is something when I did about 3 years ago, I thought first I had something wrong, but then I could prove this mathematically later. So this is the final answer. Again, the horizontal axis is the posterior probability of change obtained by a social learning. The vertical axis is the action I take, either declare no change or change, the global decision maker. So as the posterior probability of change gets larger, I declare a change, as I would. What is remarkable as it gets even larger, I change my mind and say there's no change. This is very counterintuitive. This is the optimal policy. As the probability of change gets even bigger, I say actually there is no change, but gets larger, I say there's a change. Why this multi-threshold behavior? So in other words, why is it that I have this sort of behavior where the probability which gets larger, I say there's no change? It's very counterintuitive, okay? In most standard stopping time problems, the stopping set, that is a set where my problem stops where I declare a change, is a convex set. In one dimension, a convex set is simply a connected set. So this is convex. This is non-convex because they're two separated bunches. Why is that the case? Well, that again arises because of this remarkable structure of the Bayesian update. You see, the Bayesian update here, as I told you, is having the likelihood, which is an explicit function of the prior, multiplying the prior. Okay? Now, this explicit function here is a discontinuous function of pi, obviously because my pi is taken as an argmin, which is a discontinuous function. This means that when I do a dynamic programming update in the stochastic controller, the stopping set turns out to be non-convex. Okay? And this actually is quite surprising. It also makes for a very interesting observation from a social network point of view. And the observation is this, that if I have a humans or a corporate social network where I have a bunch of workers and I get these workers to make decisions, and then I as a higher level manager use the decisions of the workers to make a global decision, it's not an easy problem. Decision making using local decisions is non-monotone. I cannot simply say that if sufficient many decisions are one way, I declare one thing, because it has this non-monotone behavior. Okay? So this is actually quite surprising. I cannot simply have a bureaucracy of lower level managers giving me a decision and making a decision easily. I need much more complex decision making skills because they have this multi-threshold effect. Okay? So this proof is actually quite complex, and it appears in my IEEE information theory paper in 2012. But the idea is actually pretty interesting, that you have a substantial difference between the way you make global decisions for change detection in a classical setting as opposed to a social learning setting. Okay? I want to make one more comment on this, and that is now how to optimize social learning, which also involves a type of stochastic control. So what we've decided so far is that social learning results in herding because every guy greedily picks a decision to minimize its own cost. Everybody is capitalistic. That's what they do, and that's why you have this kind of herding behavior. Everybody takes an umbrella because they want to prevent their own head from getting wet. And that results in herding. Okay? Now, you can think of a more different setup, which is socialistic learning. Okay? So in socialistic learning, what you do is you realize that if everybody makes a decision greedily, then everybody herds, and I cannot estimate the state because everything stops. So suppose I do the following. I choose my local decision not to simply minimize my local cost. I'm not greedy, I'm socialistic. I choose it to sacrifice my local utility so that my action provides useful information to subsequent agents. So, for example, in the umbrella problem, maybe I know that if too many guys take umbrellas, then it's going to mislead everybody to take an umbrella, so I deliberately don't take an umbrella. I make a decision, even though I might get wet when it rains. So I make a decision now to sacrifice my local utility so that for the common good in the future, people can still go on to estimate the state X. Okay? That's what socialistic learning is. So the question then would be, how do I do this? How do I decide how long do I continue the socialistic learning? So here's a very special case of that. Suppose that each time I have two choices. Okay, so this is a simplified setting. I can either reveal my full raw observation to the next guy, then I just have standard Bayes rule. In other words, I'm not optimizing a utility, I'm spending a lot of money giving my full observation to the next guy. Or I can be purely capitalistic and simply copy exactly the action of the previous guy. Okay? I'm taking a simple extreme example here just to illustrate the problem. So this is purely capitalism. This is purely altruistic. I give the guy everything they need. Okay? And suppose I want to do this. What I want to do here is to decide which one of the two do I pick at any given time so as not to minimize just my local utility, which is capitalistic, but minimize the cost of everybody. So this is a social welfare cost. This is a cost of everybody from type 1 to n, whereas this was only an individual. Okay? Now, this is a stochastic control problem because now I'm trying to control the dynamics of the system, which is the information belief pi, based on a running cost. This is a partially observed Markov decision process. This is a complicated problem to solve. In general, solving partially observed Markov decision processes are p-space hard. They need exponential cost. But in this case, using some clever mathematics, one can actually say a lot about the solution without any computation. And I want to say a couple of comments about it.
So the reward is a variable here? I mean,
the reward here is the cost of each individual based on the decision they take. Either they decide to reveal or they herd.
But ideally, I mean, it should vary because a person who's sacrificing is like, at the end, he should be rewarded more than the person who doesn't sacrifice for the social welfare.
It depends, and I'll give you an example after this where you might want to do the reverse. So if in a math finance case, you want to screw everybody so that you can make the maximum amount of money. So it really depends on the setting. Okay? But let me first come up with the solution. So this is a partially observed stochastic control problem, yet in most cases the answer you can prove has a very nice structure. So this is in my information theory paper 2011. In many cases the optimal solution looks something like this. That initially, after all I'm trying to estimate the state X, initially it's good to be socialistic so that I stop the herding and I get closer and closer to the estimate. When I get sufficiently close to the estimate, okay, I can herd because it doesn't matter, I've got sufficiently close. And this actually mimics real life. I mean, if you're a student or a faculty here, when you initially join a company or an organization, your boss is very socialistic. They give you a good startup, they treat you very nicely, but over time, of course, they expect results, and that's when it gets more capitalistic. And this is actually a very similar structure where initially it's optimal to be socialistic, and as time goes on, you want to be more and more capitalistic. Okay? So this is the structure in many cases. Another way of viewing this is saying that initially you are willing to sacrifice your privacy for the reputation of the agency. Because if you sacrifice your privacy, the agency is going to get more and more accurate in its estimate. But finally, once a reputation is sufficiently good, then you want to become more capitalistic, okay, in this case. So this is one way of interpreting this. There is actually a dual problem which you can describe, and maybe I'll just quickly describe the dual problem before I jump out of this setup. So you can imagine a thought experiment which I have not put on the slide, which is exactly related to this problem. So say I open a restaurant and I need to price the menu. How much? Do I sell stuff at a high price or a low price? If I make the price very, very high, then nobody's going to buy my stuff and I make no money. If I set my price too low, of course, I don't make a lot of money either. If I set it somewhere in between, there are two effects which happen. One of them is that, of course, people buy my product, so I make some money. The second effect, because this is in social learning, is that people who buy my product tell other people about my product. They write it in TripAdvisor and so on. So there are two effects when I sell. One is the immediate profit. The second is the propagation of the news about my product to subsequent guys who can buy stuff. Okay, and they perform social learning. You can model that by social learning. So the question then is, how do I price my product? Do I initially start up with a really discounted sale, very low, and then as more and more people come, I ramp up the price? Or do I do the reverse? Do I start really high? If I build up a loyal clientele, and I go down in price. You can prove mathematically that the optimal solution is to start high. Okay, in this case, you start as high as you can, build up a very loyal bunch of followers, and then as time progresses, you gradually decrease your price and get more and more money. Look at companies like Tesla and so on. That's what they do. Or even Apple, when they sell products, they first start high with a really good quality product to build a very loyal clientele, and then you go down. You can prove this mathematically, actually. It's a very nice argument. And again, offline, I'll be happy to discuss how you can prove this. You can then take a more sophisticated version, a game theoretic version. This was a single guy with a restaurant or a single firm like Apple. What if you had a duopoly, Apple versus Samsung? They both come up with products. Do they both start high and then go low? Because now if I start high with Apple, people might go to Samsung. And once they learn about Samsung, they may not want to come back. How do you solve that problem? So there's several generalizations of this which can, this is a basic stochastic control problem, but you can imagine a version which has a duopoly in a game where you're trying to do something. Okay, so that is how you can optimize social learning. I just have one more comment on this part one because I'm cognizant of the time. We're kind of running out of time. The last comment I just want to quickly talk about is data incest and social influence. So the basic social learning model we've done in this simple talk is where I have a linear graph. Agent 1 affects Agent 2, which affects Agent 3, and so on. In general, of course, that's not the case. Agent 1 may affect Agents 3 and 4. Agent 3 or 4 may affect somebody else, so you have a general graph. The moment you have that other sophisticated dynamics kick in, one of them being data incest. So let me explain to you what that is. So I go to a restaurant and I have a meal and I think it's pretty lousy food. So I go to TripAdvisor and write a really bad rating. So the numbers here are actually epochs. So this happened at epoch 1 time. At epoch 2, well, maybe nothing happened. At epoch 4, I wrote my rating in TripAdvisor. At epoch 6, somebody else read my rating, okay, and they went to the restaurant, and they were influenced by my rating, and they went to the restaurant, and they saw, oh, the food is pretty lousy too. And so they wrote a TripAdvisor as well, that the food is bad. Now at epoch 7, I go to TripAdvisor and say, oh, another guy said that the food was really bad. Should I really combine that guy's estimate that the food was bad with my estimate? I should not. Why shouldn't I? Because his estimate was a function of my estimate. If I were to combine it naively, then I'm double counting my estimate, because my estimate influenced his estimate. If there are only 2 people, this is trivial to solve. But if I have thousands of people on a graph with asynchronous communications, how do I do that? Well, that is really the question of how do you eliminate data incest. So data incest arises in any social learning system the moment you have a graph where you have these loops. Okay? So this is basically a Bayesian network with a loop. I have two paths to a given node, 2 sources of information. So this sort of problem is actually pretty important in online reputation agencies. Basically, an online reputation agency wants to ensure that there is no data incest. They want to maintain an unbiased blog where there is no data incest. Okay? Because data incest of this type results in misinformation. Essentially, your confidence goes up for a false event. My confidence goes up here because I think this guy also said the same thing, which is wrong because he was influenced by me. So essentially, it has a high bias, which is not a good thing for an estimator. So there's a lot of work being done in this area, and actually this is, from a monetary point of view, really important because it's been noticed that a 1-star increase in Yelp rating maps to about 5 to 10% revenue rating. So these are actually a big deal in most systems. So the question is, how do you build an unbiased online reputation system? And this can be done. I won't go into the details here. I just want to make a couple of remarks before I jump out of this slide. So we've actually studied both this and the basic social learning phenomenon amongst real humans. I mean, all this is just mathematical models, so how real is this? We did some work with the UBC Department of Psychology in 2013 where every second-year student, as part of their coursework, had to do this experiment, so they had no choice. We had about 1,000 samples in experiments, and this was the experiment we did. To each student, we took students in pairs, so student A and student B, they sit in a room. To student A and student B, each one of them, we give them this sheet of paper. This sheet of paper has a bunch of circles on the left and a bunch of circles on the right. And we ask student A which part, left or right, has a circle with a larger average radius. Say student A says left. He says it to student B. Then student B, after listening to student A, looks at the sheet of paper and then makes a decision, left or right. It comes back to student A, so the two discuss. That's social learning. Then we look at the patterns. How often do the two eventually end up concurring? Okay? That would be the case where they've made a consensus in the decision. And if one of them started differently, that means the other one influenced it. And you can pull out incest patterns that way. Okay? And what we noticed from all that was in 79% of the time, data incest patterns happen in the experiment. So humans are actually very prone to data incest. And in 21% of the time, this data incest caused individuals to change their final decision. Okay, so we have much more details of this on a paper in arXiv in case you're interested. So this actually can be verified that humans do have these sort of data incest and social influence characteristics. This is also some big deals in security defense type applications. You can imagine that there are two security guards looking at a television screen seeing if something suspicious is happening. Should they both be in the same room looking at the same TV screen and then discussing what's happening, which can possibly have data incest and herding, or should the two guys be in two separate rooms, each guy making a decision and finally they're sharing the decision? Which is the optimal route? Well, that is something which is under research at the moment because these are pretty important questions. Same thing with pilot and co-pilot in automatic decision making in the cockpit while flying an aircraft. An emergency goes off. Can some guy make a mistake which leads to the other guy making mistakes and so on? So these are actually pretty interesting problems. Okay, so that was the basic idea behind part one where we spoke about data, well, mainly social learning, but also data incest, which has these funny patterns. Actually, this also leads to some pretty interesting structure where you can imagine with social learning, you can end up with a philosophical contradiction that everybody might think that this particular nightclub is too crowded all the time, so they're not going to go there. So you can end up with the saying of Yogi Berra that nobody goes there anymore because it's always too crowded. Okay, so you can end up with some pretty interesting contradictions. And I can, again, describe these offline. There are some pretty interesting mathematical models you can do with that. Okay, so summary of part one. What we said was that social learning can result in herding and information cascades. Individuals end up blindly imitating others. In a more general setting, there's something philosophically interesting. So in signal processing, all of us believe, of course, in the law of large numbers. The more number of observations, the more accurate something is going to be. Well, what social learning is saying is if there's correlations between them, usually the more number of people, the worse your estimate is. And that's consistent with James Surowiecki's book, The Wisdom of Crowds, that usually crowds and group behavior is not wise. Crowds reduce diversity and are misleading most often. So it's kind of pretty interesting. And also data incest does things like that. Okay, so Okay, now I want to go into part 2. In light of the time, I'm just going to make a few summary comments about part 2, and then I'll conclude the talk. So part 2 was supposed to deal with large-scale social networks. In part 1, we had a small-scale network where we did Bayesian analysis. In part 2, we're doing basically adaptive filtering, or if you like, stochastic approximation over a large-scale social network. We're looking at how does information diffuse in large-scale social networks. There are very many excellent books in this area. The book Rational Herds, which I already mentioned in the Bayesian context. There's the book by Matthew Jackson at Stanford, which is really a Bible in this area, social and economic networks. It has a lot of stuff. There's another book by Redondo Vega, which is Complex Social Networks, which is also a very interesting book. This is roughly the main idea of what we want to do. We have an underlying state, which maybe might change according to a Markov chain. This is called the sentiment of something. So the sentiment might be, what do people actually think about the new iPhone 6? Is it lousy? Is it good? Let's make the simplistic thing. So there's two states in the simplistic setting, good or bad. That's the real sentiment. Now, what happens is, of course, if you're an Apple product manager who wants to know that, all you can do is simply sample from some people in the social network. I go to, for example, some product review like Yelp or whatever, and look at different things. Now, how does the information propagate in this network? By diffusion. I buy something and I review it. Somebody reads my review, they review it, and so on. So it spreads probabilistically in a social network. Okay? I sample some of the guys who are infected. Infected are people who have bought this product, for example. And then based on that, I need to construct an estimator to decide what the sentiment is. Okay? So this is truly a signal processing problem where there are dynamics in my sensor. The sensor now is a large random graph over which there are estimates propagating. And I'm getting a noisy sample of that because I can't talk to everybody in the social network. I can only sample a few guys. How do I construct an estimator? As I said at the beginning of this talk, this guy is pretty hard to analyze because it's a huge combinatorial animal. Each guy is either red or green, and the number of guys are huge, and the information is propagating. What is a way by which I can construct a reasonable model for this? I'm going to skip all this stuff for the motivation. There was supposed to be a movie here which actually shows you how you can do this for detection of flu. I'm sorry my movie doesn't work because I had to transport from... but what you would see here is the actual Center for Disease Control and Prevention of the flu outbreak in 2009. This was a social network monitored by Harvard University's Student Health Center, which is a propagation. And these are the number of tweets on that. And you would see that Twitter actually predicts this amazingly well, the 2-time series of... But there's nothing on this picture because there's no movie. But anyway, there was supposed to be a movie here. Let me skip that and go on to the basic idea. So as I said, the idea is that we have diffusion of information in a graph. If this guy is infected, then it infects its neighbors with some probability. When this guy is infected, it infects its neighbors. So really there's a Markov chain of evolution of information here. And it becomes a really complex combinatorial object. Well, one way of analyzing it, which is very powerful, is something called the mean field dynamics. And I just want to tell you quickly about it. So suppose we're interested in the fraction of agents of degree k who are infected at time n. The degree of a node is the fan-in of the node, or the fan-out. We're interested in the fraction of agents of a given degree because agents with a high degree are very influential. If I have 1,000 friends, then I'm very likely going to infect one of them. So we're interested in the degree distribution of infected agents. How does that evolve over time? Well, you see, if I count the number of infected guys and see how it evolves, that, as I said, is a Markov chain on a very large state space because this is combinatorial. It turns out as the state space gets larger and larger, this guy here looks more and more like something called an adaptive filtering algorithm in signal processing. My new degree distribution is my old degree distribution plus a small step size, n is large, so 1 over n is small, times an update plus a random term. That's how any Markov chain evolves. If you look at the expected value of this over time, over a large time scale, a martingale increment is something with 0 mean, so its expected value is 0. This becomes like a differential equation. This is like a derivative with 1 over n. And you can prove mathematically that the asymptotics of this basically become a differential equation. So without saying much more about this, the beauty of this is I can start with a really complex graph a horrible combinatorial object evolving over time and say that asymptotically, as the number of guys to go to infinity, the degree distributions converge in probability, this is called a weak convergence, to this ordinary differential equation, which is a much easier animal to analyze. This differential equation is driven by my sentiment theta t, which is my Markov chain, and now this becomes a standard Bayesian filtering problem. I have a differential equation driven by a Markov chain. I want to estimate the Markov chain. That's a piece of cake to do. It's a standard filtering problem which most signal processing people can do. Maybe I have noisy observations of that, and I can run a filter to estimate this. Okay, that's all I want to say about that. There are some references to our work recently on that. One last point. So I told you that we're trying to estimate from a social network, and what we've shown is that the social network asymptotically behaves as a differential equation. That's kind of nice. But one thing I haven't told you is you can only talk to a few people in the social network. You can't talk to everybody. So how do you sample a social network? I just want to give a couple of ideas and then I'm done. So I want to describe something called intent polling versus expectation polling in a social network. So many of you know that when an election is going to take place, there are pollsters ringing up people to predict who's going to win, and most often they're wrong. Most pollsters may go spectacularly wrong. One of the reasons why they go wrong is because they do intent polling. Intent polling is I ask each one of you here, who are you going to vote for? And then I take an average. People believe that a much more accurate way of sampling a social network is to do expectation polling. I don't ask you who are you going to vote for. I ask you who do you think is going to win. Because when I ask you who do you think is going to win, chances are you're not going to just take your estimate into account, but you're going to average the estimates of your friends. And with probability being that if you take more people, you get a more accurate sample. Okay? Not always true. It depends on the structure of the social network. Actually, expectation polling can be horribly biased. So if there are all these Democrat guys and one Republican guy, the red guy, they're all biased because each one of them is going to take the same red guy into account when you ask them. So they're going to count this red guy that many times. So it really depends on the structure of the social network. And also the variance can be higher too in many cases. So the question of how you actually sample a social network is pretty important. And there are some pretty clever tools for doing that. There's a recent paper by a couple of guys in Yahoo which show that what you would do in this case is you would weigh the red guy down by the number of outlinks. So you take the red guy to be 1/6 its weight because it has 6 friends to make it unbiased. So there's some very clever ways of doing that, which there are also Markov chain Monte Carlo ways of sampling which are used by the Center for Disease Control, which I don't want to talk about here. So anyway, that's all I wanted to say about the filtering part, where you can actually estimate the propagation over a large random graph by modeling it by a differential equation. You can sample from this graph. It's a noise, whether you use expectation polling or belief polling. And you have a filtering problem now. You want to estimate the sentiment given noisy measurements. This is basically a filtering problem. And you can do this pretty nicely. People have used this, for example, to localize where earthquakes have happened using Twitter. There's a paper in 2010. There are all kinds of stuff. People have used this for several things recently. Okay, so to summarize, in part 1 of the talk, we discussed how social learning with Bayesian processing happens in social networks of well-defined structure. And as I said, this was used by people in psychology, economics, and so on. And there were issues like herding and data incest. In the second part of the talk, I very briefly, in an incomplete sense, actually gave you some sort of idea of how you can have diffusion of information in a large-scale network, which was based on a differential equation. And I very briefly discussed a couple of polling ways how you can sample expectation and so on. As I mentioned at the beginning of this talk, this is a highly simplified presentation for obvious reasons. I mean, in 1 hour, you cannot describe a huge area. But there are several generalizations of this which are very, very important. As simple as the following idea. So if you take the basic social learning, we had agent 1 talking to agent 2, talking to agent 3, and so on. If I ask you the problem, so in the basic social learning setup, we have the agents talk in a specific order. First agent 1, then agent 2, then agent 3, and so on. Suppose I asked you, how do you optimize in which order the agent should speak? that's a very hard problem. Think about the case where a bunch of people are sitting around a table and they're deciding whether they're going to hire somebody or not. If the senior most person speaks first and says, this guy is lousy, we shouldn't hire him, he's going to affect all the junior people. So it's not ideal for the senior person to speak first. He's going to have the highest bias. If the junior most person speaks first, well, what the hell does the junior person know? He's going to have a very large variance. And so that's not optimal either. Okay? So in the US Supreme Court, for example, when judges read their decisions, it's in the anti-seniority rule. The junior most judge speaks first so that he's not swayed by more senior judges. So that's a protocol. It's not necessarily optimal, but people feel that that's one way of doing it. So in general, there is no clear defined rule when you're doing social learning to optimize the order, which is the optimal order, because individuals influence other individuals. So as I said, you can generalize these to more general graphs. I've not mentioned things like why particular YouTube videos or tweets go viral. So the dynamics of viral marketing is another big deal, which I haven't even spoken about here. Another really big deal is homophily versus contagion behavior. So in the standard diffusion of a disease, that is contagion. I get sick and I infect you, or I buy a product and I kind of influence you to buy the product and so on. Homophily behavior is completely different. It's two people have the same interest and so they do the same thing. I like chess, somebody else likes chess, so we both end up buying the same chess software, for example. So how can you tell the difference between homophily versus contagion? This is an open problem. There are still lots of interesting papers in this. So this is a really huge area, and I've simply given you some fairly straightforward highlights which are from a centric point of view of signal processing. So I want to skip this, and I just want to end up with a simple comment. This is a cartoon from Wall Street Journal which says that, it shows classical social learning, that all these guys make a decision, and the final guy says, if all you smart cookies agree, who am I to dissent, right? So I'm also going to agree, and that's pretty classical, the way things go. Okay, so here are some recent papers of mine which are centric to this talk, and as I said, these are some books which are pretty important in this area. Thank you very much.
Any questions?
So it's rather philosophical. So one of your experiments with humans showed that humans tend to herd, or they do get influenced by
incestuous patterns as well.
Right. Yeah. So if that is the case, and if we try really hard to build algorithms which tend to take those things away, and when these algorithms estimate something or predict something, are humans really going to like them?
It's a good point. I mean, so if you're considering an online reputation agency, you can give the human two things. You can tell them, here is what the estimate is based on herding and so on. Here is a separate blog which is in process, which is considered to be unbiased. Read both, make a decision. You give the human both alternatives. In more prescriptive frameworks, like in a defense situation, there you want the correct decision, right? So these are trained professionals, and there you might want to actually establish a protocol as to how the people exchange information. It really depends on a case-by-case basis. In very specialized situations, it is okay to have specific ways of trying to avoid the herding. But in general social networks, all you can do is just have a recommendation. Show people here are two alternatives. It's up to the person to choose. Yes?
You talked about the altruistic behavior and the capitalistic behavior. So have you experimented on, like, if people are more altruistic, then they achieve higher convergence in decision making rather than people being capitalistic?
So the rate of convergence is your question?
Yeah.
It's true. That's absolutely true. So in fact, I didn't mention it here, but you can actually compute the rate of convergence of a Bayesian filter in social learning. The more you reveal, the faster you converge. That's in fact shown in Shamli's book. You can actually compute convergence rates. The way you do that is, these are, after all, finite transition matrices. You can compute the second largest eigenvalue modulus, which is the rate of convergence, and you can show that the more, when you have social learning, as opposed to revealing full information, you converge much slower. Yeah. So in a socialistic environment, I mean, this is the United States. I shouldn't even talk about being socialistic, but in a sense, at least in this mathematical model, it works. I mean, in reality, who knows? This is a mathematical model. Yes?
So in the large graph that you can use the mean field dynamics to estimate the propagation. Does that depend on assumptions about the structure of the random graph?
It does actually. So you will need the graph to be fully connected, interconnected. So basically every node eventually propagates every other node with a finite amount of time. That's called recurrence. The proof of this actually is pretty easy. It uses something called the Azuma-Hofting inequality. Essentially, I look at the sum of a bunch of random guys and look at the probability that deviation is larger than epsilon. And I need recurrence in my Markov chain. Recurrence essentially means that every guy, there's a finite path from every guy to every other guy.
Nothing about like the random structure.
No. And in fact, you can do something clever there. So each guy can optimize the utility and then decide randomly which guy to propagate the information to. So the dynamics could be arbitrarily complicated as long as each guy eventually talks to everybody else. The graph is connected. Yeah.
Is that the same notion as mixing?
This is, in an abstract sense, sure. For any Markov process on a general state space, you have some form of basically Harris recurrence. This is in a more general Markov chain. That's true. But the main idea here is not so much that it's basically the convergence of a combinatorial object in function space to the trajectory of a differential equation. That's what stochastic approximation is. I have a random process, which is my combinatorial guy, and its sample path, as I'm taking n, the number of guys to be larger and larger, convergent sample path to another random process, which in this case is degenerate, it's deterministic, a differential equation. So as n gets larger, you can imagine a little tube around this deterministic guy, and I'm getting closer and closer with in probability. That's the definition of weak convergence, convergence in a function space. Yeah.
I have very other, you mentioned in the start of your slide that observations have like relationships with the future observations,
Yes.
which is like sort of dynamic evolution of
Yes.
observations, and that's why you bring this economic paradigm to do that. So, current state of the art, machine learning, like conditional random field may model those dependencies much easily than hidden Markov model. So why not
Yeah, so that's definitely true. I mean, we're trying here to come up with an analysis of what's going to happen. Now, typically when you analyze Markov random fields, in this case I'm assuming one-dimensional Markov random field over time, which is something called a reciprocal process. So we've done work on how you can use, so there's something called a Markovian bridge where I clamp the endpoint and the beginning point, and that's a one-dimensional Markov random field. It's very hard to prove dynamic programming results for that. So you can say something like simulation in those cases, but most of the proofs of how a system evolves are based on a concept called lattice programming, which are not described. They use something called supermodularity of the dynamic programming operator. They're very hard to define when you have Markov random fields. It's basically unknown. So you cannot prove stuff mathematically. But certainly from a modeling point of view, sure, absolutely, it's doable.
Okay. Well, no more questions. Let's thank our speaker.